Hi, my name is Valiye. Me and my group mate Sena Mushtaba Pelin. We worked on a cone beam city simulator. In this project, we applied a cone beam city on two different data sets, and we also applied some noise to see the result. As the name express, our beam is cone shaped. The cone beam CT scanner is used when we need 3D images. It's not commonly used because it has a lot of energy and can cause some difficulty for the patients. Our method had two stages. First, we project data, and the second one is backpropagation. We use two different data sets, global and MRI head phantom. In this slide, you can see the resolution of our data sets.
Okay, so in the projection part, in the 3D phantom is taken as an input, and one of its 2D slices is especially taken as an input, and the output is one of the 2D projection of the slice, and this is repeated for every slice of this 3D phantom. And also the 2D interpolation of the coordinate system in Z and Y axis is taken for every one of these 2D slices so that the result is correct. And the projection formula used is given below, where the projection equals the source times the detector times the radius of source and times the source angle, and all of this is divided by the radius of detector times the detector angle.
The second method that we used in our project was back projection. We used filtered back projection, which is an algorithm for reconstructing the image from their projections, which requires measuring the integral of the image intensity along two specific directions. This algorithm is commonly used in CT imaging, where a beam of X-rays is passed through a patient and the attenuation of X-rays is measured as they pass through the body. But we used a specific algorithm of this filtered back projection, which is FDK. The FDK in cone beam CT, the X-ray source and detector rotate around the patient and creating a conical X-ray beam that passes through the patient. The FDK algorithm takes into account the conical nature of the X-ray beam in order to reconstruct an accurate image of the patient. There are advantages of this FDK, which is it has lower artifacts and noise in image that we produces, and it can be relatively slower than other algorithms, but the iterations but thanks to iterations we get better results.
So in the project we used two different phantom datasets, which is the original Zubul phantom dataset and also the MRI head phantom datasets. And from these two different results were obtained for each of these datasets. And one of the results obtained has noise and the other has no noise. And also the effects of changing the distance between the source and the detector are also shown in the results. So here our first results can be seen. This is from the original Zubul phantom dataset. And in the left side you can see one of the example Zubul phantom slices. This is slice 100. And in the right side you can see the projection. This projection is taken from the angle 0 to 360. You can see the whole Zubul phantom shapes. And here you can see the results again, but this time with noise. Here you can see the projection results for the 360 angle. Again, these projections are taken from 0 to 360 degrees, but this time noise makes it difficult to see the body shape. And here you can also see on the right side noisy back projection. This again taken for the same slice, but this time it's difficult to see the shape of the slice. And again, these are the results, but this time for the MRI head phantom. On the left hand side you can see the MRI head phantom, which is the example slice, again chosen as slice 100. And again the projection results can be seen taken from the angle 0 to 360. And also, you can see the projection and back projection results for the angles. Here you can see the projection result is noisy, but you can still see the brain. And on the right side, you can see the back projection results, and the contrast and the resolution of this image is lower compared to the original slice. Here you can see the results of the changing the distance between the source and detector. The distance is decreased, and so the projection image is smaller, and because of that the back projection image is noisy. And here you can see the following results obtained by increasing the distance between the source and the detector. Because of that the projection data is very noisy and does not make any sense, and the back projection data is wrong.
When we compared noisy result and non-noisy result, we observed that noise decreased the resolution and the contrast of the image. To avoid noise effect, level of radiation can be increased. When we change the distance parameter between source and detector, we observed that image quality becomes really bad. When we increase distance, we obtain empty image. And also when we decrease the image distance, we obtain meaningless result. So we should set up distance properly to obtain meaningful results. I think it's done.